Today we're going to shift gears quite a bit, actually, and move from momentum, which is kind of an extension of Physics 20, right? Mechanics from Physics 20. We're going to move on, start talking about electricity today, something that's just a little bit more abstract than the momentum unit. We can't physically see the electrons moving around and so on, but we can see the results of electricity pretty concretely. As the year goes on, we do tend to get a little bit more abstract. Magnetism in our next unit, electromagnetic radiation in our unit after that, and then finally we have atomic physics towards the end. So we're starting to go on that little slide towards the more abstract here with electricity. What do you see up on the board here right now? What is this? Knowing the context of the unit here, what is that? Yeah, it's an atom. It's a diagram of an atom, right? Or it's a simple diagram of an atom. What is it that we have in the middle of this atom? It's the nucleus, yeah. And in the nucleus, we got what? We got protons and neutrons, and of course, how many protons is what determines the type of atom that we have. We know that those protons inside the nucleus are going to be positively charged. We've also got the neutrons. We're never going to pay, well, I shouldn't say that. In our last unit in atomic physics, the number of neutrons sometimes becomes important, but until that time, we're never going to mention neutrons again, okay, until our last unit. In this unit, the neutrons are completely irrelevant. In this unit, the protons are almost irrelevant. When we're talking about electricity and how electricity flows and how electricity builds up and so on, we're not talking about protons. We're talking about these things that orbit around the protons and neutrons, which we call electrons. Electrons are these negatively charged things that orbit around. Why do you think it is that we're talking about electrons that, in the context of this unit as opposed to protons? Why is it that if something's going to build up or if something's going to move around, flow through a light bulb and cause a light bulb to turn on, why do you think it's going to be electrons versus the protons? Yep. I'm sorry?
Because in the transfer of energy, electrons are transferred.
Yeah, but why is it that electrons can transfer between atoms versus protons? You're absolutely right. But why is it, like fundamentally, why is that the case? Why, when we transfer that energy, why isn't it protons that move? Why is it electrons that move?
Because if we move the protons, you make a new atom.
Yes. Okay. If we change the number of protons in an atom, we actually change the atom itself into something else. It's called transmutation. That's actually a nuclear reaction. Yeah, and typically, when you rub a balloon against your hair, you're not causing a nuclear reaction. Okay, protons just don't move. They can, but generally they don't. Generally, it's electrons. But why is it that we don't move protons? Why is it that we don't change the atom into something else when we rub a balloon against our hair? Why is it that the electrons know to move, but the protons know to stay where they are? You had your hand up a second ago there, Julia. Good. They orbit around. You use a term there. I'm not sure if you use it perfectly, actually. I'm not sure if you realize you use it perfectly, but I'll get to that in a second, okay? But you're right. They orbit around the nucleus, and they're not as tightly bound to the nucleus as the protons are. You mentioned something called the strong force. Did you mean to say that, or? Okay. It's funny because actually there's an electric force that causes the electrons to be attracted to the positive nucleus. Positive attracts negative, right? We all know this. Positive attracts negative. That's an electric force. Sometimes we call it an electrostatic force. But there's also something called a strong nuclear force, which sometimes we just call the strong force, that actually acts between protons and neutrons, that keeps that nucleus really, really tight together. It doesn't want to break apart. That proton doesn't want to leave the nucleus. It can in certain circumstances, but it doesn't want to, so it doesn't usually leave there. It's a way easier for the electrons to break free of this electric force than it is for the protons to break free of this strong nuclear or strong force that's in the nucleus. So why is it that we talk about electrons and almost never protons in this unit? Well, it's because electrons are going to be the things that move around. And they're going to be the things that move around because they're not nearly as tightly bound to the nucleus. They're attracted by an electric force, but that strong nuclear force is way bigger, at least in that context, is way bigger, so the protons have a much, much harder time leaving. We need to have a lot more energy put into this than rubbing your hair in order to cause the protons to leave. Does that make sense? So, we're talking about moving charges in this unit. It's going to be electrons. Okay, it's going to be the electrons that move. Now, I said we almost never talk about protons in this unit, but we do a bit. We do have to a bit because we have to understand where positive charge comes from. If I rub a balloon against my hair and the balloon becomes negative and my hair becomes positive, it doesn't mean that my hair has just protons, but it does mean if my hair has become positive, then it has more protons than electrons. Do you guys understand the symbols that I use there, proton and electron? It has more protons than electrons. Now, that also doesn't mean that it's gained protons, because the protons aren't going to move anywhere, right? They're too tightly bound to the nucleus by that strong nuclear force. It means the electrons have moved somewhere. So, if you've got positive charge, then what's likely happened is that you've lost electrons. Not gained protons, but it probably means that you've lost electrons. And if you have something that's neutral, which has no charge, and you take away negatives, then you're going to be left with something that's positive. Negative charge comes from, well, just the opposite. It comes from having more electrons than protons. It doesn't mean we have just electrons. There's going to be some protons there as well, usually. But we've got more electrons than protons. And of course, that's going to come from having, for some reason, gained electrons. If we start off with something that's neutral, which has an equal number of protons and neutrons, something that's neutral, let's say, sorry, not protons and neutrons, but protons and electrons. The neutrons are irrelevant because they're already neutral, right? Let's say we started off with, 5 protons and 5 electrons. To make that positive, we would lose an electron or 2 electrons or 3 electrons. And maybe now we've got 5 protons and 2 electrons. Okay, that gives us a net charge of plus 3, positive charge. Notice the number of protons hasn't changed, but yet it's become positive. Now, on the other hand, if I had 5 protons and 5 electrons and I gained electrons, maybe it became 7 electrons. Now we've still got 5 protons, but we've now got a total net charge of negative 2 because we've added negative charge to it. The unit of charge, this is a new one for you. Okay, we haven't seen a new unit for a while. Even in our last unit, the unit for momentum was kilograms meters per second, but we were familiar with kilograms, and we were familiar with meters, and we were familiar with seconds, right? Okay, we're not familiar with this one. The unit for speed is meters per second. The unit for time is seconds. The unit for mass is kilograms. The unit for charge is the coulomb. Named after a guy who did an experiment, did several experiments, but one that we're going to talk about later on in the unit, Charles Augustin de Coulomb. You do some important stuff, you get a unit named after you. Now, if I asked you, if I gave you a problem in Physics 20 or even in Physics 30 in Unit 1, momentum, about speed, and I gave you a speed of 50 kilometers per hour or a speed of 100 kilometers per hour, you would have at some level an intuitive notion as to what that meant, right? How you'd be able to visualize a car at 100 kilometers per hour, or you'd be able to visualize a car at 50 kilometers per hour, or a person running at 15 kilometers per hour, or whatever the case may be. Okay, we'd have a notion. We could see it in our minds. Okay, we could see what a kilometer per hour really is. We can't see what a coulomb is. We have no concept of what a coulomb is, right? How big is a coulomb? How big is a kilometer per hour? We know this from experience, but we don't know how big a coulomb is. Well, let me give you some perspective. Okay, the charge of an electron is negative 1.60 times 10 to the minus 19 coulombs. And the charge of a proton is positive 1.60 times 10 to the minus 19 coulombs. Now, what does that really mean? Well, it means a coulomb is a pretty big unit because an electron has a very, very tiny amount of coulombs. In fact, you don't have to write this number down. I'm going to write it in green. You can skip writing that down if you want. But in order to get a full coulomb of charge, you would need approximately this many electrons or protons. That many electrons gives you a coulomb of charge, or that many protons gives you a coulomb of charge. So that's a big unit, right? A coulomb is a big unit of charge. It takes a lot of electrons or a lot of protons to give us that unit of charge. In fact, it's so big that we often see the unit for electric charge given as microcoulombs, 10 to the minus 6 coulombs. Or we also sometimes see it as a nanocoulomb, which is 10 to the minus 9 coulombs. Remember, if you see those, microcoulombs or nanocoulombs, which you probably will fairly often, you got to still convert to coulombs in order to do calculations because that's our base unit. It's just that because it's such a big unit, we often don't see it expressed that way. We have to do that conversion ourselves. So be ready for that. Right? We saw that in Unit 1 with speed and kilometers per hour convert to meters per second and mass in grams converted to kilograms and so on. We saw that, but in this unit we tend to see a little bit more because a coulomb is such a big unit. Take a look at your data sheet here, either the one at your desk or the one that's up on the board here. I gave you the charge of an electron. We need to know the charge of an electron, but we don't need to memorize it. Okay, that's something that we can easily look up. Take a look in the top right-hand corner of your data sheet. See where we find the charge of an electron. Okay, we've got a bunch of different particles listed, including an alpha particle. We saw an alpha particle once in our last unit. We didn't know what it was. I didn't explain to you what it was. I'm not going to explain to you now what it is. Okay, that's going to come in our last unit towards the end of May. An electron, well, we know what that is. A proton or neutron. Then we get these first-generation fermions. Electron again. Positron, electron, neutrino. Those will come in our last unit as well. I want to focus on these ones here right now. Electron, proton, and neutron. What's the mass of them? Well, an electron you can see is 9.11 times 10 to the minus 31. You ever need that information? It's on your data sheet. A proton is way heavier, like 1,000 times heavier. In a neutron, you can see at least at 3 digits, a neutron has the same mass as a proton does. Beyond that, it actually doesn't. Okay, a neutron is a slightly different mass than the mass of a proton. Let's look at the charges. Minus 1e, plus 1e, and of course 0, neutral. What does the e mean? I just told you a second ago, didn't I, that the charge of an electron was negative 1.6 times 10 to the minus 19 coulombs. Now we're saying it's minus 1e. E stands for something called the elementary charge. That elementary charge is going to become more familiar with you in our last unit as well. But for now, I'm just going to tell you what the number for the elementary charge is. It's over here. The elementary charge is 1.6 times 10 to the minus 19 coulombs. So if you have a charge for an electron of minus 1e, then it would be minus 1 times 1.6 times 10 to the minus 19 coulombs. Or a proton would be plus 1 times the elementary charge. Look, that information is on your data sheet. You just got to know where to find it. Okay, when you get a quiz or a test and you need the charge of an electron in coulombs, and you look at your data sheet and you see that it's minus 1e, you need to know how to convert that to coulombs. And that's simply by multiplying it by 1.6 times 10 to the minus 19. All right? And it's hard to imagine, by the end of the year, all of this stuff, including on the other pages of your data sheet, becomes familiar to you. You know it all by the end. Man, doesn't this sound hard? A fermion? It's not that bad. It's not that bad. Okay. Let's look at a few different ions here, just as quick little examples of what the charges would be here. This is Al3 plus, aluminum, right? Or what do they call it now? Isn't it aluminium or something like that now? Yeah? I think it's aluminium, isn't it? Is that what they call it now? I don't know. Whatever. Al3 plus means, what's the charge of this Al3 plus, aluminum or whatever it's called now? Well, I mean, it doesn't mean that it has just 3 protons. It means it has 3 protons more than electrons. So it doesn't mean you've gained protons, it means you've lost electrons, giving you a positive ion. The charge of this would be 3 times 1.6 times 10 to the minus 19 coulombs. It's 0.8 times 10 to the minus 19 coulombs. And this one would be, well, this is just Na plus sodium 1 times 1.6 times 10 to the minus 19 coulombs, which of course is just 1.6 times 10 to the minus 19 coulombs. What about this one? O2 minus? This one would be, follow the pattern, minus 2 times 1.6 times 10 to the minus 19 coulombs. So the charge of that would be negative 3.2 times 10 to the minus 19 coulombs, which it got from gaining a couple of electrons as opposed to losing a couple of protons. Remember, can't lose the protons, right? Can gain electrons, it can't lose the protons. Protons don't move anywhere. How come? Because of that strong nuclear force that keeps it together. Whereas electrons, they get that electric force, but not quite as strong, that far out at least. Okay, let's take a look at a quick example. This question says a balloon is rubbed against hair, gaining a charge of negative 9.6 times 10 to the minus 9 coulombs. So you can see there, right? An electron is 10 to the minus 19 coulombs. There's a lot of electrons there, but you can still see we have a pretty small amount of coulombs. This would be 9.6 nano coulombs, or 9.6 times 10 to the minus 9 coulombs. How many electrons has the balloon gained or lost? We're never going to say how many protons has it gained or lost. We're going to say electrons, right? How many? Let me give you a little analogy here to maybe make this a little bit easier to understand. Let's say that Blake goes to Safeway and buys some oranges. He buys a bag of oranges. Let's say the bag doesn't weigh anything, just for argument's sake. Compared to the oranges, it doesn't weigh much, right? It's effectively zero. Negligible, we call them. Blake buys his bag of oranges, doesn't know how many oranges are in the bag, but he does know the bag of oranges weighs 3 kilograms. So 3,000 grams. Thank you. He weighs 1 orange, and 1 orange weighs 500 grams. It's a big orange, heavy orange. Like a really heavy orange, actually. But we'll use that. So 1 orange weighs 500 grams. He has 3,000 grams of oranges. How many oranges has Blake bought? 6. How'd you get that? Division, right? We said 3,000 divided by 3,000 divided by 500 gives me 6. So we took the total mass and divided it by the mass of 1 orange to give us the number of oranges. We're going to do something similar to find out how many electrons the balloon has gained or lost. The number of oranges was the total mass divided by the mass of 1. The number of electrons will be the total charge. Charge, by the way, given by the symbol Q, a lowercase q. The total charge divided by the charge of 1 electron. So we're going to say the total charge here is negative 9.6 times 10 to the negative 9. And the charge of 1 electron is negative 1.6 times 10 to the minus 9 coulombs. Total mass divided by mass of 1 gives me the number of oranges. Total charge divided by the charge of 1 gives me, that should be negative 19, shouldn't it? divided by the charge of 1 gives me the number of electrons. So 9.6 times 10 to the minus 9 divided by 1.6 times 10 to the minus 19. Gives me 6 times 10 to the 10. There's a lot of electrons. Well, it's 10 to the 9, 10 to the negative 9 coulombs. Of course, it's going to be a lot of electrons. Charge of 1 is 10 to the minus 19. Remember this. Whenever you're looking for a number of anything, take the total and divide it by the amount for 1. Total number of oranges, total mass divided by the mass of 1. Electrons, total charge divided by the charge of 1. Later on this year, in our second to last unit, you're going to look for the number of photons, whatever a photon is. You're going to take the total energy divided by the energy of 1. So it's always the total divided by the amount for 1, whether it's mass or charge or energy or whatever it is. Now, one more little question here before we're done with this. Have the electrons been gained or lost? Has this balloon gained electrons or lost electrons? We say it's gained a charge. That doesn't mean it's gained electrons, right? Something that loses electrons also gains a charge. Has this gained electrons or has it lost electrons? The balloon was neutral. Now it's negative. To become negative from neutral, you have to gain negative. You can't lose positive. You have to gain negative. So this would be 6.0 times 10 to the 10 electrons. Oops. Gained. Does that make sense? This is how we charge things, right? We cause the electrons to move around, and we do that by, well, there's a few different ways that you're going to learn tomorrow. One of them is rubbing things together. Okay, you rub your balloon against your hair, and it becomes, well, the balloon becomes negative, your hair becomes positive. Sometimes there's one pair of dress pants that I have. When I put them on, they always stick to my legs. Okay, the hair on my legs gets all staticky and causes either the pants to become negative or positive. I'm not sure whether the electrons leave the pants or they go to the pants. I don't know. I'm not sure. What I do when I put those pants on? Static guard. Okay, what's static guard? Basically alcohol. Okay. You spray it on your pants, what happens? The alcohol either loses electrons and they go in to neutralize the pants, or it gains electrons to neutralize the pants, depending upon what the pants were, right? Negative or positive. If the pants were negatively charged and that's why they were sticking to my legs, well then we're going to lose electrons from the alcohol and then it's going to go into my pants to neutralize it. If the pants were positive, then we need to gain some electrons from the static guard to neutralize the pants. Make sense? Why do you think we'd use alcohol? Why not water? Like if you sprayed water, wouldn't it have the same effect? Absolutely. So why do we use alcohol? So they can charge money for it? Partly probably, but water would work. Water would work just as well. But why do we use alcohol versus water? Because alcohol evaporates a lot quicker, right? So you don't have wet pants. So if I'm got staticky pants and I go back there into the storage room and spray my pants to get them unstaticky, I don't want to come out here with soaking wet pants. Okay, because that's just as bad as having staticky pants. Okay, make sense? All right. Now, we're going to do just a little bit more here, guys, and we're going to do a break, and then a little bit more after that, and then we'll call it a day. Two terms. A conductor in the context of electricity, okay, we know that we can have a conductor in the context of heat as well, but that's something different. In the context of electricity, a conductor is a material in which electrons in the outermost regions of the atom are free to move. Like the electrons, it's always easier for the electrons to move than it is the protons to move. But in some materials, it's easier for the electrons to move than it is for other materials. As a general rule of thumb, what materials have electrons in their outermost region that are freer?
Copper.
Copper's an example, yeah. But as a general rule, we're usually talking about metals, right? Copper's a great example of a conductor. Some metals are better conductors actually than copper, but copper's a very good example of one. Some metals aren't as good, but generally speaking, metals are good conductors. Versus other materials that we call insulators, where the electrons aren't as free to move. They're pretty tightly bound to the nucleus. Doesn't mean they can't move, but they're not as free to move around from atom to atom within the substance. So we say in this case it would be an insulator as opposed to a conductor. But understand it's kind of a continuum, right? It's not like we have a firm line that says, okay, these things allow conduction and these things don't. It's like a spectrum where you've got really, really good conductors and then conductors that aren't quite as good and then conductors that aren't very good. And then we're getting into insulators which can still conduct, just not nearly as good as the category that we call conductors. Everything will conduct. Everything that's got electrons will conduct. Some things just not very well. Now I'm going to flip the page here. I'm not going to ask you to copy this table down. Okay, I just want you to look at it. Okay, we'll go through it just briefly just so that you can kind of get an idea as to difference between conductors and insulators. If you look at the top of the page here, gentlemen, you can see that we've got these things listed as conductors. And what do these things for the most part have in common? Yeah, they're metals, right. Silver, copper, aluminum. Silver, you can see, is a better conductor than copper, right? Well, we use copper to conduct electrons in our houses, right? Why don't we use silver? Because it's a lot more expensive, right? There's some other reasons as well, but primarily because it costs a lot more than copper. Copper's gotten pretty expensive, though, too, over the last 10 years or so. So expensive that, in fact, it sounds odd, but people actually go and steal copper so they can sell it to scrap metal places. Like it's gotten to the point where there's actually been people electrocuted trying to steal copper. Right? Let's try to steal wire so we can sell it to a scrap metal place and make some money. That's how valuable copper has become. Still not nearly as valuable as silver or gold, right? Gold, by the way, is a fantastic conductor. Okay, whenever you buy an audio cable, sometimes, what does it say? Yeah, sometimes it says gold-plated. More expensive ones tend to say gold-plated. And why? Well, because gold's a really, really good conductor. Now, it's only gold-plated, so you start wondering how much of a difference that's going to make because the rest of the wire isn't gold, right? It's only the plating of it that's gold. Okay? Gold is a really, really good conductor. Aluminum, we use copper wiring in our houses now. Aluminum, or aluminium, or whatever you call it now, we used to use aluminum wiring in our houses. We don't use aluminum wiring in our houses now, not because of the cost, not because of the conductivity. It's almost as good of a conductor as copper. Aluminum had this habit of arcing. When you had two wires inside your wall close together in your house, it tended to arc from wire to wire. And what's the problem with that? Well, your house would burn down. Sorry? Yeah, or any metal, really, in the microwave. But so we don't use aluminum anymore, even though it's almost as good of a conductor as copper. Is not quite. Iron, mercury, Metals, right? And then down here, what do you see for insulators? Wood, glass, rubber, right? Things that you'd associate with not conducting electricity. Now you see some numbers on the left-hand side here. These numbers are irrelevant as far as you're concerned. I just want to point out that what they mean. They're relative conductivities. So if we say, let's say somewhere in the middle of our, we call it semiconductors, is 10 to the 0 or 1. Okay, 1. Well, then this silver is 10 to the 8. So like it's 10 to the 8 as compared to 1 is a much, much, much better conductor, right? Even if we're talking about mercury down here, which is about like 10 to the 5, okay, it's still a much, much better conductor than a semiconductor here. But then we go down to, say, rubber, 10 to the minus 14, 10 to the minus 15. Okay, does rubber conduct electricity? Sure. You're wearing rubber-soled shoes. Try standing outside in a lightning storm with an aluminum baseball bat. Okay, try to taunt the lightning into striking you. Okay, see if the rubber-soled shoes really help you much. Let me give you a little hint on that. They won't. Even though rubber's not a great conductor, it'll still conduct electricity. Lightning will easily go through the rubber-soled shoes into the ground, right? Rubber will still conduct. Wouldn't be quite as bad, though, as if you were wearing copper-soled shoes or something like that, right? Either way, I think you're going to be pretty much dead, but you'd be dead a little bit quicker wearing copper-soled shoes, that's all. Does that make sense? Those numbers you don't need to remember. And even like the order of these, don't worry about that. But just remember generally metals versus non-metals. Okay, copper versus wood or glass. Okay, this is almost it, guys. Almost it. We have 3 laws of electric charge that you're somewhat going to be familiar with already. Then we're going to talk about one more law that we call the law of conservation of charge, and then that's going to be it for us. 3 laws of electric charge. Opposite charges attract. We know this, right? Positive attracts negative. Negative attracts positive. Like charges repel each other. All right, positive repels. What does repel mean? Push away from each other, right? And the third one, be careful with the wording of this. Charged objects attract neutral objects. That word objects is important there. Here's why. I said a little while ago that protons will attract neutrons in the nucleus, but not by an electric force. The electric force doesn't cause protons to attract neutrons. On the other hand, if you have a positively charged object and a neutral object, they will attract each other. In other words, you've got to have a whole bunch of protons and a whole bunch of neutrons that give you a positive object and a neutral object in order to get an attraction there. Okay, a simple positive proton will not attract a simple positive neutron, unless it's by a strong nuclear force. Then it will, but not by the electric force. So charged objects will attract neutral objects, but positive won't attract neutral and negative won't attract neutral. You're going to see why tomorrow. Okay? Got to leave you with some kind of cliffhanger, right? Okay? Tomorrow we will see why charged objects will attract neutral objects, but positive will not attract neutral. Protons won't attract neutrons. Last one. Last page here, then we got a little example, but we've already got that handed out to you. The law of conservation of, well, let's go back to the law of conservation of energy that you learned in Physics 20. Energy can't be created or destroyed. Transformed from one type to another, but can't be created, can't be destroyed. The law of conservation of matter. Matter can't be created or destroyed. The law of conservation of momentum. Total momentum stays the same, or momentum can't be created or destroyed. The law of conservation of blank. Blank can't be created or destroyed. So what do you think this is going to say? Charge can't be created or destroyed. It can be transferred from one to the other via electrons moving. But we can't create charge that wasn't there, and we can't destroy charge that is there. Even though it seems like it sometimes. 5 and negative 5 gives me 0, but I haven't destroyed anything. I've just transferred them. Here's a quick little example that's in the handout that I gave you a little bit before, a little bit ago. It says two charged objects of similar size, similar shape, and similar material. They momentarily touch each other. Sometimes it doesn't say this, but in order to make this work, we have to have similar size, similar shape, and similar material. Here's the deal. When you touch two objects together, we get charging taking place. The electrons will transfer from one to the other. The goal is to balance them out. So if I have a charge of 0 and I have a charge of -5 and I touch them together, the goal is to balance out to be -2.5 and -2.5. But if one of them is way bigger, one of the objects is way bigger, then it can actually hold more charge than the other one. Or if one of them is pointy, it can hold less charge than the other one. So in order to make them balance, we would say that they were similar size, similar shape, similar material, so that they can balance out. Okay, so the first object initially has a charge of 2 times 10 to the minus 6 coulombs, and the second one is negative 3. When they touch each other, what does it become? Well, if 0 and 5 balance out to be 2.5 and 2.5, what are we doing there? How do we figure that out? 0 and 5 gives me 2.5. Add them up and divide by 2, right? Average them. So what are we going to do here? Average them. 2 times 10 to the minus 6 plus negative 3 times 10 to the minus 6 divided by 2. Negative 1 times 10 to the minus 6 divided by 2 is negative 0.5 times 10 to the minus 6, or 5.0, negative 5.0 times 10 to the minus 7 coulombs. So that's what they balance out to be. Now, which object gained electrons? The one that was positive and became negative, right? It was 2, it became negative 5. The one that gained electrons was the one that was positive and is now negative. The one that lost electrons is the one that was negative and became less negative. And it was 3 times 10 to the minus 6. Now it's only 10 to the minus 7. Is that okay? If we're positive and we become negative, we must have gained. If we're negative but we become less negative, then we lost electrons. And our last example, it says ball 1 initially has a charge of 3 coulombs. 1 touches 2, which is initially negative 1. 1 and 2 are separated, then ball 1 touches 3, which is a charge of minus 5. What's the charge on each one of them afterwards, after all this touchy-feely question? Similar size, similar shape, similar material, so everything wants to balance out, right? Well, because we got different events going on here, we gotta kind of treat it as separate problems. Let's make a little table. Ball 1, ball 2, ball 3. Initially, 3 coulombs, minus 1 coulomb, and minus 5 coulombs. It says 1 and 2 touch each other. 1 and 2 touch each other. 3 plus minus 1 gives me 2. Divide that by 2 to average them out gives me 1. So we're going to find that this becomes plus 1, and this becomes plus 1. What does this one become? It hasn't done anything yet. It hasn't touched anything yet, right? So plus 1, and minus 5. Now it says ball 1 touches ball 3. So now we got 1 touching 3. 1 and negative 5 averages out to give me minus 2. 1 plus negative 5 is minus 4, divided by 2 is minus 2. What does charge number 2 become? Stays 1, because nothing's happened to it this time. So final charge on each, minus 2 coulombs, plus 1 coulomb, and minus 2 coulombs. Assuming they can balance out because they have similar sizes, similar shapes, and similar materials.